This is section 5.2, the definite integral, content objective 4, which is to use the graph of the integrand and areas to evaluate definite integrals without a calculator. When we're done, I'd like you to be able to explain why the area between a function and the x-axis can have a different value than the function's definite integral. To motivate this, I want to think about the integral of a constant. If f of x equals c, where c is a constant on the interval from a to b, then the definite integral of c with respect to x from a to b will equal that constant times b minus a. To consider why this works, let's look at this first graph where c is a positive constant. The accumulation from a to b of that constant with respect to x will be exactly the same as the area of the rectangle. And the area of the rectangle is the height, which is the constant value c, times the width, which is b minus a, or the length of the interval. So if we apply that here, we would get the height, which is 5, times the width, which is 11 minus 3. We'd end up with 5 times 8, or 40. With this one, our height would be pi, and the width would be 5 minus a negative 2, and we'd end up with 7 pi. If, on the other hand, c is a negative constant, then this accumulation from a to b of c with respect to x will be the opposite of the area. So let's say this is our origin right here, so c is underneath the x-axis. That accumulation will be a negative number, so the area will be the opposite of that c times b minus a, which means it will be the opposite of the integral. So again, the integral, or the accumulation, will be that negative number times the 11 minus 4. We'll have a negative 3 times 8 is a negative 24, which is the opposite of the area when our constant, or our horizontal line, passes through y equals negative 3. If we look at b, same thing. We will have the constant times the width of the interval, which is 2 minus negative 5. We end up with negative 7 root 7. This relationship between the integral and areas are going to hold true even when f is not a constant function. If the function f lies above the x-axis, then the accumulation is positive and it will equal the area between the x-axis and f. On the other hand, if f lies below the x-axis on the interval from a to b, then the accumulation from a to b will be a negative number that will be the opposite of that area. This relationship allows us to use our old geometry formulas to compute definite integrals exactly. How we'll do this is we will first graph the integrand and find its zeros, and then the accumulation from a to b will equal that area above the x-axis minus the area below the x-axis. With example 1, we're going to compute the definite integral from negative 3 to root 5 of a with respect to a. Because this is the same as this one, that means that the variable is going to be a. This is not a constant. Typically when we see a's, we treat them as constants, but the fact that we have a dA at the back tells us that we're dealing with a variable that is a. So what we've graphed here is an input that is a and an output that is f of a that equals a, which looks an awful lot like that y equals x. If I want to compute the definite integral from negative 3 up to root 5, we need to look at the area below and the area above. Well, this is a triangle whose area is 1/2 the base times the height. This has an area of 1/2 the base times the height. So the area above will be 5/2 and the area below will be 9/2. So we end up with an overall accumulation of negative 4/2 or negative 2. If we look at example 2 to compute the accumulation from negative 5 to 0 on this with respect to r, we need to know that this is the equation for the upper half of a circle. So for those of you that have forgotten that, we would have f of r equals the square root of 25 minus r squared. Well, that's kind of the same as saying y equals the square root of 25 minus x squared. If we square both sides, we'll get here, move the x's and y's together, and there's our equation of the circle that hopefully you recognize from both geometry and algebra 2 and pre-calculus. So since we have just the positive root, we're just getting the positive half of that circle, and we're only accumulating from negative 5 to 0. So that means we're getting that left quarter of the circle. If I want the accumulation, notice that all the area is above the x-axis, so it will be 1/4 pi times a radius squared, and we end up with 25 pi over 4. With our last and final example, we want to use the graph of the integrand and areas to evaluate this. Well, 3 minus the absolute value of x is a v that has been turned upside down and then moved up 3 units, which we see right here. We want to find the area that is below and the area that is above. So below, looking at this, we can see that it's a triangle. So that'll be a 1/2 the base, which goes from -3 to -4, so that's a 1, times the height. Well, the height of that is going to be 1, because if I plug -4 into this, I have a 3 minus a 4, which is a -1. The length of that will be 1. If we look up here, there are several ways that we can approach this. Some people will do the entire triangle here. So that would be 1/2, a base which is 3, and a height which is 3. And then they'll add the rectangle, which is a base of 1 and a height of 2. And then the triangle, which is 1/2, a 1 times a 1. So we'll end up with a positive accumulation that is 9/2 plus 1/2 plus 2, and we'll have a negative accumulation of 1/2 as well. So the 1/2 will cancel. I'll get 9/2 plus 4/2 gives me 13/2.